So I'm interested in this, and one of the challenges and one of the reasons that software security exists is there's lots and lots of bugs out there, but only some of them are of security significance. Which ones? If you go look at Linux, we know that there's 100,000 known bugs in Linux today. I also know with the simple 6-line programs, I can go find dozens of more new bugs in about 15 minutes. It's the sort of thing you can do on a break if you really want to. And most of those are of, little security consequence, but some are quite deadly. And so, which bugs are exploitable is the research question that I focus on. And our vision is to figure out which bugs are exploitable automatically. In fact, we want to check the world software for exploitable bugs. And it's something that we're going to be working on for a long time, our team. Our basic approach is based upon binary program analysis, where we take an off-the-shelf executable, the same executable you'd run on your computer, and we do program analysis. And while traditional program analysis would output one of two things, whether it's buggy or safe, we want to add a third output, whether or not we can find an exploit. And our techniques are based upon a variety of different program analysis. And previously I focused on something we called automatic exploit generation. I've given that talk many, many times. So today I want to tell you something new. In the past year we've been focusing on fuzzing. And the reason we focused on fuzzing is because it's a relatively easy, cost-effective thing to do. And it tends to work pretty well. So we've been working about 12 months on this. And the idea is that you do fuzzing, which triggers crashes in programs, and then you give the output of that to automatic exploit generation, which will determine whether the crash can be turned into control flow hijack, something that would allow an attacker to take control of your computer. And we've also been working on that for a number of years. We are one of the people who introduced the community to this concept. And luckily, it's actually taken on in recent years. If you look at things like the Cyber Grand Challenge, a core concept in DARPA's Cyber Grand Challenge is can you automatically exploit software? But today I'm going to focus on fuzzing. I'll point you to the work on automatic exploit generation. If you haven't seen it before, it's great stuff.
We need meetings for interaction and to make sure that all these teams, really interdisciplinary teams, ranging from people with law degrees all the way to software developers, understand and are on the same page. But it really makes the compliance problem immensely difficult, especially at this scale where we have millions of lines of code in the pipeline and rather complex policies about how those pieces of code operate on personal information. So instead, we completely redesigned this workflow to take the same teams, but to make their interactions much more streamlined through two technical contributions. The first is a language that we call Legalese, and that's not a spelling mistake. And the goal of Legalese is that it's a privacy policy specification language. It serves as an interface between the legal team and the software developers. The legal team, we designed it in a usable, in a form that's rather usable, and people in the legal team and the privacy champions can encode their English language policies into this language. The second component, the second technical component is something that we call Grok. Grok is a data inventory. It annotates existing code via automated code analysis and some amount of manual annotations with the kinds of constraints that the privacy policy imposes, so that after we have the annotated code, and completely automated information flow checker can take the annotated code, take the Legalese policy, and check if the code respects the policy. And flag potential violations, which can then be reviewed by the audit team. If it's a real violation, then that goes back to the developers on how to fix the code, where to fix it. In some cases, we can get false positives because this data inventory is not perfect, in which case there's a feedback to the inventory to fix, to update information about the annotations. So to summarize our findings, we have this new workflow for privacy compliance, which includes Legalese, which is a usable yet formal policy specification language. The reason to have a precise policy language is to enable automated enforcement. And then this inventory that we call Grok, that bootstraps existing code for big data systems with policy labels. And then we have a scalable implementation for for Bing, and the prototype tool that was produced is now running on their production system. There is an ongoing adoption effort inside of Microsoft.
And most recently this year, I think this is in April, some people find some malicious extension that hijack your cyber wallet, your cryptocurrency, and so on. So the goal of this research, essentially, we're trying to look at this Chrome extension architecture. We're trying to systematically study all the possible attacks can be mounted by these extensions. So essentially, we're trying to look at, so in Chrome, the protection is by permission system. We're going to look at the permission system and figure out what are the ways that the Chrome extension can abuse the system so that they can gain your private data. So we actually look through the Chrome store, look at all the popular extensions, and we look at what percentage of the extensions can be potentially dangerous, or they're given the permissions that can do harm to you. This research is actually a stepping stone for us to move, to go forward. So once we figure out what's the problem with the existing architecture, what we really want to do is that we're trying to develop new mechanisms so that we can mitigate these dangers. We want to build a better browser, a better security architecture, so that we can prevent a lot of these attacks. So that's actually the final goal of this line of research.
One of the first questions is the security of a CPS an issue, right? If we have good cybersecurity, is that sufficient? Right. I claim that there is a distinction between cybersecurity and CPS security, and I think the main difference is the presence of a physical system. Dealing with physical systems introduces some new challenges. When we talk about security to apply to physical infrastructure, we really talk about safety, about resilience, and so not necessarily want to. Our goal is not to protect the information system and guarantee availability, integrity. Of data, but that could be a tool. But really, what we want to protect is the physical system. Also, when you deal with physical system, there's an issue of inertia that is not as visible and as present in pure cyber system, right? If you realize the computer is compromised, you turn it off, right, and then you deal with it. If you have a physical infrastructure, like an airplane that is flying, that you realize has been compromised, right? You don't have the luxury of just turning the system off, troubleshooting, and then bringing it back on. You have to continue operating under attack. Guaranteeing what we call graceful degradation. You remove certain ancillary services, but you want to guarantee the main one, that for instance, the plane flies safely. Also, patches might be more expensive in the physical world. I think with challenges, fortunately, there are all sorts of opportunities as well. And the physical systems have the luxury of following very precise physical laws, for which we have good models, right? You can use the predictive power of these models to infer something about the system, whether the system is operating correctly or not. And so what I advocate is to use models and their good predictive power to develop tools which are system theoretic tools to address the issue of security in cyber physical systems.
And the reason they deploy them is because they provide these kinds of capabilities that they cannot achieve with their Cisco and Juniper routers and switches. So there's a lot of value in these boxes because they serve a key role in the infrastructure. But at the same time, sort of our talks and our discussions with network operators suggest that there's a lot of pain points in them sort of working with these middle box devices today. The first pain point that operators have told us, and we've had a long discussion with many of these network operators, is that these boxes are simply too expensive, right? So they have to buy a firewall, and it costs in sort of north of hundreds of thousands of dollars, and it also adds to the clutter in the network. So every time they need a new functionality, they have to go buy a box and plug it and patch it into the network. So it kind of creates a lot of network clutter. A second problem with these kinds of specialized network appliances is that it actually increases the management complexity of a network. In fact, the large enterprise network from which the table comes from, they actually have like separate teams for managing and tuning and configuring each class of network appliance. So they have a firewall team, they have a WAN optimization team, they have a load balancing team, they have an IDS team, they have a VPN team, and so on. Because sort of each kind of these kind of functionality comes with its own crazy configuration protocols and so on. So they need to really understand the low-level details of each of these boxes, and that requires separate management teams for each of these functions. And the third, and perhaps sort of a more significant challenge for them, is that once they buy this fixed hardware and they plug it into the network, it's kind of this, they're sort of committed to this, and it creates this inflexibility in the network. So for example, many enterprises are moving towards this sort of bring your own device attitude, like where you want to let your employees bring their own laptops, bring their own tablets and phones and so on. So naturally you need like some kind of security infrastructure to make sure these sort of employee-owned devices come inside the network. Now the only way for a network operator to sort of react to this trend is actually to go and buy new boxes, like you buy an iPhone gateway, you buy an Android gateway and so on. And the reason is that sort of the existing infrastructure cannot be easily extended to add new functionalities as your application landscape changes. And there's also an even bigger problem is actually that these are actually difficult to upgrade. So there's a little bit of irony here. So when Heartbleed came out, one of the problems people perceived is that actually they have a network security infrastructure like firewalls and proxies and so on that were actually running vulnerable versions of OpenSSL. And those were actually much more difficult to upgrade than your traditional servers, because this is like, it's almost like doing like a firmware upgrade, and it requires the vendor to come and support and patch this. And this could take months. Whereas if you have a commodity server, you just run the software update and you're done. So it's almost like ironic that your network security infrastructure becomes your vulnerability when you have vulnerabilities in the software stack of these things. So sort of the status quo today is that these are a critical piece of the network security infrastructure, but they kind of have this high cost, high complexity, and they're difficult to extend to add new features. So both in terms of upgrading them to react to vulnerabilities, as well as sort of adding new functionality to react to changing applications and changing threats.
So one of the primary threats we're worried about is that due to globalization of both the hardware and software supply chain, you have on the left there a map of where your system goes to get built, designed in the US and then partially designed someplace else. The CAD tools are designed someplace else. You pull in IP from all over the world. You manufacture it maybe in the US, maybe in Asia, maybe in Europe, and it goes around and around. And finally, after all of those routes, you get a fully designed hardware system. Right? Inside of that design, we're pulling in third-party IP blocks. So, if you buy a processor from Qualcomm or something, it's not like a Qualcomm engineer designed every single piece of that piece of the core processor, that they've gathered up pieces of it from all over the world and from third-party makers and then pulled them in together. Right? The tools themselves are usually built by a third party. There's some internal tools, but not very many of them. And finally, on the application side, you're running the OS and applications from all over the place as well. Now, very specifically, one of the threats that hardware roots of trust are made to counter is counterfeiting.